Okay, greetings. Welcome to this lecture. So, previous lecture, this is where we stopped. Like we were looking at this concept of closed loop control system with feedback, and we discussed a few points associated with this overall block diagram. This course, like is essentially built on this, right? So when we talk about control, like by default, we are going to talk about closed loop control with feedback, and we are essentially going to learn, like how to design this block controller. Okay, so the primary focus of this course would be to, okay, let me not put an arrow, like circle, right? So the question becomes, like we are given a plant or a system. Let's say in the example that we are considering, let's say a vehicle whose steering has to be controlled. How do we design, like the controller so that like the closed loop system should be stable and should meet some specific performance requirements. Okay, so if you recall our course on vehicle dynamics, initially in the course of vehicle dynamics, we would have learned about stability and also performance by looking at race time, settling time, and so on, right? So similarly, we are going to look at the closed loop system, like, and then we are going to see how the closed loop system, like can be designed such that the overall closed loop system is first of all stable. Then second, it should meet some performance requirements. So that's something which we are going to learn as we go along in this particular course. Okay. So let me continue from here, and then like we will learn some more concepts now. So if you look at the overall problem of control system design, right? So if you look at this overall domain of control systems or control system design, if we look at it, like depending on the phase in which activities happen, right, or the theory was developed, like people would essentially split it into what is called as classical control and modern control. So this is, of course, a very standard way of categorization, like, but I'm going to explain what this is, right? So what is this classical control, right? So what happens in classical control is that, like, if you recall, we would have learned about transfer function and so on, right? So the classical control design method is based on the transfer function. Okay, so we use the notion of transfer function to design controllers as far as classical controller is concerned, and we do the analysis in the S domain or the complex domain, right? So in the classical control design method. Okay, so that's classical control. And what happens in modern control? In modern control, we do design based on the state space representation. I think we had a brief introduction to the state space representation in vehicle dynamics. So we will learn a little bit more about this in this course. Okay, we will use the state space representation to design controllers. Of course, here we are not going to use the Laplace transform, but rather we stay in the time domain itself and do the design. Okay, so that is the idea, right? If we look at how come there are these two broad categories, and why is one is called classical, one is called modern? So obviously, one may get an idea that like it has to do with the time period over which these techniques were developed, and immediately one can observe that we are going to have classical control techniques which came earlier and followed by modern control, right? If we look at the objectives, classical and modern. right? So it so turns out that, like around 1950s, 60s, right, is when the transition happened. This was primarily driven by the invention of the integrated circuit, right? Digital electronics and so on came into play around 1950s, 60s, and with that, like it also revolutionized the way controllers were implemented. Previously, control systems were implemented using analog devices, analog circuits, and so consequently, even the design methods, okay, were based on using the transfer function representation and doing the analysis in the complex term. Then, when the invention of the integrated circuit and semiconductor devices propelled the adoption of digital electronics, the analysis in the time domain, okay, became more feasible and practical, and obviously there were relevant developments, okay, wherein people looked at utilizing this invention to the advantage as far as implementing control systems was concerned, right? So that is the broad reason why these are called classical and modern. In this particular course, we are going to learn about classical control. We are also going to learn about modern control. Okay, so we will learn both these methods. Okay, but first we will learn about classical control. And of course, one may get the question, hey, what about automotive systems? Okay, which branch of control, okay, from this perspective is used, okay, in automotive control application? So the answer would be that it is essentially both. Okay, it really depends on the application and the problem under study. Okay, it is just that in some cases, like one may use modern control to our advantage. In some cases, like classical control may be more advantageous. Okay, so there is no unique choice per se. Okay, depending on the application, like one may select either one of them, right? So that is the okay. So essentially, moving on, as I mentioned, initially we will look at analysis using classical control tools, and then we will study about modern control. Right? Okay. So let me continue. So if we look at classical control, it's based on the transfer function representation. So I'm just going to briefly recap what we had already studied in vehicle dynamics, okay, on this notion of transfer function. So if you recall what a transfer function was, it is the ratio of the Laplace transform the output to the Laplace transform the input under zero initial condition, right? So if you recall the general this is all like recap. I'm going to go a little bit faster, okay, just to refresh our memory. Okay, the general governing equation of nth order so LTI causal dynamic system can be written as the following. Okay, A naught dny dtn. I'm sure we recall this general form, plus A1 dn minus 1 y dtn minus 1 plus all the way till an minus 1 dyt plus an y of t. So these are the terms in terms of output and the derivatives. Then we have terms involving the input and its derivatives. So we have d naught du, the m derivative of u, plus d1 dm minus 1 u of t d dt m minus 1, okay, plus all the way till d m minus 1 du dt, then plus dm u of t. Okay, so this is the general equation. So if you recall, it characterizes linear systems because the ODE is linear in time. Okay, and it is time invariant because all the coefficients are constant; they are independent of time. Causality is reflected in the fact that the value of m is greater than or equal to m. All right, so it's a single instance, right? So what we do is that, like, we apply the Laplace transform on both sides, and take z and apply and consider zero initial. Right, this is the definition of transfer function, right? Is it not? We apply the Laplace transform, and then we substitute all initial conditions to be zero. So by default, we are not considering the free response of the system, right? We are interested in only the forced response, okay, of the system under state. Okay, so that is what we are going to consider. All right. So if we do this and then we cross multiply, we get the plant transfer function or the system transfer function, which is going to be equal to y of s by u of s, which is going to be equal to b naught s power m plus b1 s power m minus 1 all the way till bm minus 1 s plus bm divided by a naught s power n plus a1 s power n minus 1 all the way till a n minus 1 s plus. Okay, so this is the plant transfer function, right? So this is something which we are familiar with, right? And we recall that in general, the plant transfer function is a ratio of two polynomials in it, the numerator polynomial and the denominator polynomial. The numerator polynomial is of order m, okay? The denominator polynomial is of order n, right? So that's something which we, all right? And we have what is called as a proper transfer function corresponding to causal system. In a proper transfer function, the order of the denominator polynomial is greater than or equal to the order of the numerator polynomial, right? So that's what we have for a proper transfer function, right? So, and strictly proper transfer function means, like we are going to have the numerator polynomials order to be strictly less than the denominator polynomial, right? So essentially, what happens is that, like, if we look at the this one, right? Anyway, we essentially consider the ratios of the two polynomials. If n is strictly greater than m, then we have a strictly proper transfer function, right? So what happens is the following. So if we have this is the definition of transfer function. So if we cross multiply, we are going to get y of s equals p of s times u of s. Then we will be able to see the advantage of using the transfer function. That is, if we are able to find the transfer function p of s, then given any input, we should be able to find the corresponding output, right? So that's something we can certainly do, right? And as we have already discussed, the roots of the numerator polynomial n of s or what are called as the zeros of the plant transfer function, right? P of. Okay, and there are m zeros, right, as far as the transfer function, because the numerator polynomial is of order n. Okay, so we essentially that to be the case. And if you look at the roots of d of s, they are called the poles of the transfer function, right? So these are the poles of p of s. and there are M poles. Okay, all right. So these are some terms which all of us are aware of, and we have also studied some standard inputs, right, and the corresponding output for the response function, right? So standard inputs that we would have run are the unit impulse, right? Once we provide the unit impulse, we get y of s to be equal to p of s, right? So for that reason, the Laplace inverse of p of s is also called as the impulse response. So that's something I'm sure all of us recall. Okay, so in fact, from an application perspective, if we are able to provide an ideal impulse input, we should be able to figure out the transfer function, right? So that's the implication there, right? So the unit impulse is a standard input. We also have a unit step as a standard input. Okay. We also have unit ramp and sinusoidal input. Okay, so these are all standard inputs that we use to steady system response. Okay, so that's something which all of us are familiar with. Okay, so once again, for u of t to be, if we give the unit impulse input, u of s is 1. This implies that y of s becomes equal to p of s. And if we take the inverse Laplace transform, y of t becomes equal to p of t, right? Where the Laplace of p of t is equal to p of t. So this is the reason why p of t is what is called as the impulse response. Right? So this is just a quick recap. Okay, we should remember that. All right. Okay. Okay. So this was a very quick recap about transfer function and of a generic system in the class of systems and study. What are the recap of the concept of poles and zeros, and then we also looked at some standard inputs that we provide and corresponding responses. Like that we essentially use to look at the output of the system, right, and analyze them for the response. So that's something which all of us are aware of. Now, if we just do a quick example so that like we refresh our memory. So let us consider an example. Okay. So let us consider second order system. Whose governing equation is y double dot t plus 3 times y dot t plus 2 times y of t is equal to u of t. Okay. So let's find the transfer function. Pole zeros and then unit step response. Right. So let's just recap. So let me do the entire process once so that like we refresh our memory, and then like we should be able to carry on, right? So essentially the governing equation is y double dot t plus 3 times y dot t plus 2y of t is equal to u of t, right? So that's the governing equation. So we take the Laplace transform on both sides. So if you take the Laplace transform on both sides, what do we get? I'm just going to write the complete Laplace transform once. I'm sure all of us recall that the Laplace transform y double dot is going to be s squared y of s minus sy0 minus y dot 0, right? That is the Laplace of y double dot. Then we'll have plus 3 times s times y of s minus y0, right? Plus 2 times y of s is equal to u of s. Okay? So that's what we have. Then, as we know, we take all initial conditions to be 0. So y of 0 becomes 0. Y dot of 0 becomes also equal to 0, right? So we consider all initial conditions to be 0. So doing that, what do we get from that? If we do this, what's going to happen is the following. We'll have s square plus 3s plus 2 times y of s is equal to u of s. So that will imply that the Planck transfer function p of s, which is going to be equal to y of s divided by u of s, going to be equal to 1 divided by square plus 3s plus 2. Right? So this is pretty straightforward. Okay. All right. So now immediately one can observe that the value of n is equal to 2. Right? So consequently, the poles are nothing but the roots of the denominator polynomial, right? So in this particular case, the denominator polynomial is s squared plus 3s plus 2. So consequently, the poles are at -1 and -2. And the numerator polynomial order is 0 in this case. So there are no zeros to begin with, right? So as far as this particular system. And if you recall, typically we will essentially illustrate the poles and zeros graphically using the S-plane, a complex plane where we plot the real and the imaginary axis. This is our S-plane, and let's say this is our origin. And if you recall, we illustrate the poles using an X, and the zeros using a ZO. So in this particular case, the two poles are at -1 and -2. Okay, so that's essentially the transfer function. Okay, so now we need to find the unit step response, right? We have found the poles and zeros, so we need to find the unit step response. So we essentially consider u of t to be equal to 1. So then this implies that u of s becomes equal to 1 by s, right? So if we do this, now we can go ahead and calculate the y of s. Okay, so y of s is going to be equal to p of s times u of s. This is going to be equal to 1 divided by s square s times s square plus 3s plus 2. This can be rewritten as 1 divided by s times s plus 1 times s plus 2. And we can rewrite this as a by s plus b by s plus 1 plus c by s. Okay, so that's how this could be rewritten, right? So essentially, we do the partial fraction expansion, right? So that's what it is called, and where a, b, c are what are called as the residues, right? So how do we find a, b, c? Do you recall the process?
Yes, sir. By putting s is equal to 0 once, by putting s is equal to -1, and by putting s is equal to -2.
Very good. Yeah. Before that, we also need to multiply by the corresponding factor, right? That's right. So let me illustrate once. So suppose if you want to find a, what we do is that like we multiply both sides by s, right? So what will we get? We will get 1 divided by s plus 1 times s plus 2. That's going to be equal to a plus bs divided by s plus 1 plus c times s divided by s. And then we substitute s equals 0, right? So that's what. Correct? So once we do that, we get a to be equal to half, right? So essentially, we multiply both sides by the term which is in the denominator of the term corresponding residue and substituting its root. So similarly, if we were to find b, we multiply both sides by s plus 1. What happens is then we get 1 divided by s times s plus 2 is equal to a times s plus 1 divided by s plus b plus c times s plus 1 divided by s2. And now we substitute s equals minus 1. Okay, when we substitute s equals minus 1, what do we get? We get minus 1 will be equal to b, right? And if you want to find c, we multiply both sides by s plus 2, right? We will have 1 divided by s times s plus 1. That's going to be equal to a times s plus 2 by s plus b times s plus 2 divided by s plus 1 plus c. Then we substitute s equals minus 2, which is the root of this term. Then we get 1 by 2 to be equal to c. Alright, so this is how we calculate the residues. Okay, please note that A, B, C are called as residues. Okay, in the partial fraction. Alright, so this would imply that y of s is equal to 1 by 2n minus 1 divided by s plus 1 plus 1 by 2 times 2. So this will mean that y of t will be equal to 1 by 2 minus e power minus t plus 1 by 2 e power minus 2t. So this is what we get. Okay. So here as t tends to infinity, we can observe that y of t tends to 1 by 2. And we recall that the poles appear as the exponents, right, in the response function. Okay, so that's something also we need to recall, right? So when we are right, so note that the poles appear as the poles appear, right, as the exponents of the exponential term in the response function. Okay, so that's what, right? Okay. Now, if you look at what to say, this entire process of control system, then there was a quick recap, right, of an example that we are already familiar with. You know, like, we should be using such techniques, you know, like even in the analysis and design of control systems. Okay. Yeah. So one important advantage in classical control system design process is that like we can what to say use these methods, you know, that are associated with you know, complex algebra. You know, like we can essentially process the system equation in the complex domain where ODEs become algebraic equations, and then we use inverse Laplace transform to come back to the time domain. Okay, and we will see how we are going to use those processes. Okay, as we go along. So if we look at control system design, as such, and we are looking at a closed loop system, once again, these two things become extremely important. Okay? Stability and then performance. Right? So, what is this notion of stability? You know, like, you know, vehicle dynamics course, we would have learned about what is called as bounded input, bounded output stability, right? So, We are going to learn about two notions of stability in this particular course as we go along. Okay, so sorry, we are going to learn about Vibov stability. This is what you would have we are already familiar with. Okay, and we will also look at stability of an equilibrium state. Okay, so there are going to be two notions of stability that we are going to utilize in this particular course. The first one is on Vibov stability. The second one will be on what to say, stability of an equilibrium state. Okay, so those are two notions of stability that we shall consider in this particular course. So if you recall what was Vibov stability, so let me quickly recap bounded input, bounded output stability. So what was Vibov stability, if you recall? So the notion of bounded input, bounded output stability requires that the system's output remain bounded for all possible bounded input, right? So that is the notion of Vibov stability. So consequently, if you provide any input that is bounded in magnitude, then the corresponding output also needs to be bounded in magnitude for all time. Okay, so that is what is the notion of bounded input, bounded output stability. All right. So the question becomes, what was the corresponding criteria, right, for that? And that's something which we also learned. I will quickly recap that. So a system, of course, the class of systems under study, right? A system is Vibov stable if its output is bounded in magnitude for all time and for any bounded. Okay, so okay, so that's something. Okay, so as we have already learned, the equivalent criteria is that the necessary and sufficient condition for a LTI causal dynamic system to be Vibov stable is that all poles of its transfer function lie in the left of them. Right? So lie in the LHP. Okay, so that's something. Right? So if you recall, what was this LHP? Like if I go back briefly to this S-plane, please note that the imaginary axis is going to split the complex plane into two half planes. So what is called as the left of complex plane and the right of complex plane, right? So in the left of complex plane, all values of S have negative real parts and the right of complex plane, how to say, any value of S has a positive real part, right? And the imaginary axis serves as a boundary, right, separating these two orbitals. Okay, so the necessary and sufficient condition for Vibov stability is that all the poles, like of the system transfer function, lie in the left of complex plane. Okay? So that is the necessary and sufficient condition. So if you look at the Planck transfer function, if we consider, write it once again as a ratio of two polynomials, n of s and d of s. So essentially, we are looking at the roots of the polynomial d of s, right? So some people will say the necessary and sufficient condition is that like d of s should be Hurwitz. So what does this term Hurwitz mean in the context of a polynomial? It just means that the roots of all the polynomial of the particular polynomial in question should lie in the left of complex. So let me write down the definition. Okay, so a polynomial is said to be Hurwitz if all its roots have negative real. Okay, so that's the definition of a polynomial being Hurwitz. Okay, so the complement of this thing is that if even one pole lies in the right of plane, the system is going to be unstable, right? And we also had looked at what happens if we have poles on the imaginary axis, right? Suppose if we had non-repeating poles on the imaginary axis with uh, all the other poles in the left of plane, the system's output was bounded. System's output is unbounded only for certain bounded inputs, right? So for example, if we have a non-repeating pole at the origin, when we give a step input, the output becomes unbounded, right? So if you have a non-repeating pole at, let's say, plus or minus j omega, the output becomes unbounded only for cos omega t and sin omega t, right? So consequently, people call that case as the system being marginally stable or critically stable. Okay, so but as I discussed, of course, that is one from the perspective of Vibov stability. When we look at the another notion of stability, you will also gain a subtle distinction and understanding as we go along. But as we discussed in our vehicle dynamics course also, right? So it doesn't matter even if the output is unbounded for one bounded input. Some may call the system as unstable. So the choice is left to you. Typically it's called as critical stability or marginal stability, with understanding that it's not stable in the Vibov sense, but it's almost Vibov stable, right? Yeah, but that is not good enough, right? So as far as practical application of control. All right. So we shall look at the other notion of stability, that is stability of an equilibrium state, and then we shall connect the two, right? And we will see what is the equivalence between the two, right? And another important point is that when we have repeating poles on the imaginary axis, it does not matter. For all bounded inputs, the output is going to be unbounded. So the system is unstable. Okay. So if we have repeating poles on the imaginary axis with all poles, other poles lying in the left of plane, the system is unstable. Okay. So these are the four cases that we have looked at. All right. So as far as stability is concerned. Okay. So what I will do is that I'll stop here for this particular lecture, and in the next lecture we will recap about performance. Okay, before we go on to control. Right. So what I'm going to do is that in this particular lecture, I briefly recap about transfer function representation and stability. Next lecture we will recap about performance specification. Then we will carry on with the analysis towards control design problem. Okay, fine. So any questions? Okay, so let me stop recording and then we'll continue next.